Okay, why don't we begin? So today's speaker is Shivani Dantabarua, and she's an assistant professor of mechanical and aerospace engineering at Illinois Institute of Technology in Chicago. And she received her Bachelor of Science in Physics and MS and PhD degrees in Aeronautics and Astronautics from Stanford University. Before joining Illinois Tech, she was a research engineer at Astra and then an assistant professor of aviation at San Jose State University. And she has received the NSF Career Award and the Institute of Navigation Powering Early Achievement Award for outstanding contributions to the understanding of the dynamics of the ionosphere and its impacts on satellite-based navigation integrity. And she's on the NASA Living with the Star Program Analysis Group, the ION Council, and the UNAVCO Geodetic Infrastructure Advisory Committee. And her main research is the use of global navigation satellite systems for remotely sensing Earth's atmosphere and surface, tomography and data assimilation for prediction of the ionosphere and thermosphere dynamics, and mitigation of upper atmosphere effects on GNSS-based navigation systems. And today she will present mapping material transport in the upper atmosphere with Lagrangian coherent structures. Go ahead, Shivani.
Great. Thank you, Nick, for the introduction and the invitation. Thank you all for being here today. I would like to talk about a project that my lab's been working on for several years, and I'll be showing results and development of numerous students from my lab. So I'd really like to credit all of them, as well as NSF, NASA, and some undergraduate research programs. I've sort of had undergrads, graduate students, PhDs, and postdocs sort of working on different aspects of Lagrangian coherent structures. So I'll go over the concept of why we might be interested in material transport, talk a little bit about what I mean by coherent structures before giving a little more detail on Lagrangian coherent structures, or LCSs, which are really quantified through this finite time Lyapunov exponent. So we'll talk more about that. Our algorithm for doing these calculations is called italics, and I'll show you some results, what we found in the charged layer of the atmosphere, that's the ionosphere, and then the thermosphere as well. And if there's time, this last little bit of ongoing work we have working with finite domains rather than a global spherical atmosphere. So just to kind of ease us in, I'll just point out that the last space shuttle launch was actually about 10 years ago now, and it would launch from Florida. All the shuttles did, and it would launch into low Earth orbit. And so that's not vacuum of space. It would go up through the layers, past the troposphere, the stratosphere, beyond the mesosphere, 50 to 85 kilometers, and up in towards the lower thermosphere. That's neutral particles. And in that layer, charged particles also exist. This constitutes the ionosphere. And at about 100 kilometers altitude, it would, the main engines would essentially deposit 300 tons of water vapor, very high altitude, into the atmosphere. And so previous researchers, in particular Stevens et al., have used these shuttle launches and observations subsequently of the water vapor to connect it to the presence of Noctilucent Clouds. Those are polar mesospheric clouds that shine at nighttime because they're at such high altitude. And these were found over the Arctic. Now, this is not a picture specifically from that shuttle event. This is just this is an image of data from the NASA AIM mission. But the idea is that water vapor and where it goes, or any material and where it goes in the upper atmosphere, matters for various reasons. Whoops, I seem to have gone backwards. Let's try that. And so the question is, could we have had any indication that space shuttle exhaust, the water vapor, could was going to end up in the Arctic, or would it have been constrained and limited from going into the Arctic? And so the idea behind this is to think about that material transport in a fluid structure. So in a fluid, transport can be sort of described by, or is governed by, coherent structures. And so here in this picture, these pictures from the Haller review paper, these are kind of intuitive examples. On the left is an image of the Deepwater Horizon oil spill. So you've got an offshore oil rig, and you can see the plume of the water, of the oil on the surface being carried along by the ocean currents in this particular confined area. It doesn't spread out evenly everywhere. There are certain regions where it does or does not go. And then on the right-hand side, this is essentially a water over the ocean vortex. And so that's kind of what I mean when I'm sort of indicating coherence in a fluid material. So in the upper atmosphere, coherent structures matter for a number of reasons. We might be interested in looking at the environmental impact, as oceanographers or ecologists might be interested in, for tracking emissions, contaminants, chemical species. We might be interested for the effects of the transport of those materials on our technological systems, so space weather effects. And so I'll talk more about how ionospheric plasma is of interest, because it can impact communications, radio communications, and radio-based navigation systems. And we're also interested for the scientific understanding that we're interested that we can gain from understanding better what's happening in the stresses created in the fluid, vorticity, thinking about how energy is being transported within that fluid, or transferred within that fluid. So here's, so people, fluid dynamicists have worked on defining coherent structures for a long time now. And there are kind of two frameworks for following fluids. One is sort of the Eulerian frame, or the Eulerian viewpoint, where you set up a fixed grid and you watch the fluid flow past you. And so there are some definitions of fluid structures, vorticity or something like that. They can be quantified through parameters describing of that fluid, properties of that fluid, but they will tend to depend on the observer's motion itself. So what that means is that the coherence that you see is kind of depends on who's looking at it and how that person or that observer is moving. So as an alternative, Lagrangian descriptions of coherent structures are meant to be invariant. I think the technical word that is used is objective. It means they are independent of the observer's motion. Independent of translations and rotations that the observer, the person who has set up that grid or that frame is using. So the question that we have been asking and investigating in this work is, what are the Lagrangian coherent structures in the upper atmosphere? So that's really the name of the game, to kind of look at computing those, finding those, and seeing if they have any significance for our understanding of the upper atmosphere. So I'll start off here by just giving kind of some illustrative examples of an LCS with sort of cartoon flows. So on the left, you can see a snapshot of a flow field. And this is kind of a flow field that's a double gyre. You kind of have these two counter-rotating vortices. And basically, if you have particles in that flow, right down the middle, there's kind of a dividing line between particles that will be circulating in the vortex on the left and particles that will be circulating in the vortex on the right. And so that dividing line, that structure, is the Lagrangian coherent structure. So if you think about, so it sort of defines the perimeter of where the one vortex ends and the other one begins. It's sort of the separation barrier there. And so in the bottom plot, I'm showing the LCS in this with this blue to yellow color scale. And the LCS is that vertical line down the middle. And if we set up tracer particles, A naught in red, B naught in white, and C naught in pink, and we trace them through the flow over time. So each one of these is showing a different location at a different time. Then A naught and C naught, those are to the left of the LCS, those stay in the left vortex. And B naught, which is to the right of the LCS, stays to the right, in the right vortex. And so that's the idea behind the Lagrangian coherent structure, that it shows you dividing areas between where flow is going to qualitatively behave differently. So the example on the left was for a time invariant double gyre. These two flows, that snapshot is a description of the velocity field over all time. If instead you have a time varying flow field, then let's say this vortex is, the two of them are alternatingly expanding and contracting. So this is the first time instant, and then the second time instant, the third, and back and forth. And they're sort of alternating periodically. Then there's still an LCS in the flow, but now it's not quite so obvious which particles will end up in which vortices. So, but there is still an LCS there. So the LCS in this particular case for the time varying flow is this yellow ridge that runs up the middle, curves right, and arcs around to the left. And so that LCS is essentially this yellow ridge in 2 dimensions, or it would be a surface in 3 dimensions. And it describes that where the flow is undergoing the maximum amount of separation. And if you run it, you can also do a calculation to find where there's maximal convergence as well. And so in this example, A naught and C naught, they do stay over here to the left, and B naught is over on the right, because again, they're separated by that LCS running between A naught and B naught. So the way that you actually compute these, I sort of showed you the maps of them, but didn't quite describe how we get those. This is all theory that's been developed in the fluid dynamics world over the past several years. We start off by thinking of the flow map. The flow map is basically a function. You can think of it as a function or a mapping function. And it takes an initial particle. You start your particle at x naught, and you trace it over time. If you know the flow fields over time, the velocity fields over time, then you can trace it to where it ends up at some later time. So it's just the mapping from starting at this location to ending up at another location, x. Okay, so that's just integrating the velocity over the time over that particle's trajectory. So that flow map sort of describes how the entire domain might be distorted. But if you pick a particular x naught, you can linearize that flow map and say, well, I know what the location would be exactly at x naught, but if I went a small distance away, delta x naught in the domain, how far off would my final position be? And so that can be Taylor expanded essentially. And so that would give you the location, the final location f of x naught plus effectively the first derivative here, which I'm writing with the nabla operator, the gradient operator of f, dotted with delta x. So the interpretation here is that an initial perturbation away from x naught will produce a variation in the final position. So if we want to look at how the final positions change, that delta f, given some initial offset in the distance, delta x, then what we're interested in is this, the first derivatives of f. And so that gradient, or actually really what it is a Jacobian matrix. It's a Jacobian of the flow map. So these cartoons will try to, I'll try to describe this. So again, the Jacobian is the linearization. It's a matrix of the first derivatives of the final position's coordinates given small changes in the initial position coordinates. So I have two coordinate, for a two-dimensional flow, I have two coordinates. I'm going to use superscripts to designate the coordinate direction. So x1 is my horizontal coordinate, x2 is the vertical one. And I'm interested in small deviations away from x naught, which is here at the location x1 naught and x2 naught. So I will consider small deviations away, delta 1 along the x direction. So that'll give, I'll look at the black dot on the left and the gray dot on the right. And small deviations away in the vertical coordinate. So that's delta 2 distance away, and that's the red, and minus delta 2 would be the pink. And so I take that, I take the flow fields, so as long as I have some specification of what the velocity fields are over this whole domain, I can take my each of my particles, the black particle here, trace it over time, and it ends up at some final location. I take the gray particle, trace it over time, and it ends up at another final location. So I can measure how far apart in the horizontal direction those final locations are. So df1 here is in black, is indicated with the black arrow, and df2 is here between the blue arrows. I can do the same tracing calculation with the red and the pink. So I take the initial particles, trace them through the flow to some final locations, red and pink shown here. And I get some final horizontal separation with the red arrow here, and in the vertical direction with the purple arrows on the right. So what this is essentially doing is showing me how that, another way to think of it is how the unit sphere is kind of going to stretch and deform. And so we can arrange all those partial derivatives of where the particle ended up given a small offset in the first coordinate into a 2x2 matrix. Okay, so at each point x naught, I get a 2x2 matrix in a 2D flow. I would get a 3x3 matrix in a 3D flow. And so those differences that I showed with the black arrow and the blue arrow, those are the numerators of each of these elements in the 2x2 matrix, the red and then the purple. And then you difference by the, you do a center difference by the initial delta offsets. So this 2x2 matrix is describing the deformation. And so if you take that matrix and you're interested in the magnitudes, you would take that 2x2 matrix, transpose it, and multiply it by itself. And that corresponds to what's called a Cauchy-Green deformation tensor. And you can look at and you can compute the eigenvalues of that matrix. So it's going to have two eigenvalues. And we define we're interested in the largest eigenvalue. That shows the amount of the maximum stretching. And so that largest eigenvalue, we sort of normalize it using a natural log and divide by the integration time. That largest eigenvalue, I'll call it sigma, that is what we define as the finite time Lyapunov exponent. And so that's related to considerations of dynamical systems where you consider, if you linearize a dynamical system and you look at its time evolution, you get the eigenvalues driving the exponential behavior of the modes of that system. So in those figures I was showing earlier, I was plotting in color bar with the color scale the finite time Lyapunov exponent, the FTLE. And the LCS, then we can identify as that maximum value of the FTLE through this whole domain. So the color map is the FTLE value. It shows us where the maximum amount of separation is happening. And where that maximum separation is happening, that's the Lagrangian coherent structure. Yeah, so the other thing I want to mention is that it's important when you do this integration that you think about the T naught, the starting time, matters for a time invariant flow, a time varying flow, and how long you integrate for also matters. They're going to change the shape, location, and structure of the LCS depending on those choices of your integration. So on the right, I had previously shown what the Lagrangian coherent structure looks like for the time varying double gyre if you start integrating at t equals 0. But if you start integrating with the different initial time, so you might think, well, okay, A naught, B naught, C naught, these are not so useful because they look exactly the same. They have the same similar movement to the time invariant double gyre. But what's useful is if you look at particles over here in the upper left, there it's not obvious. If you just look at a snapshot of the flow, you might say, oh, okay, well, they're all going to start off, they're all going to be going to the right. So sure enough, they do all start off going to the right. But A and B, which are on the same side of the LCS, both end up in the right half of the flow. And C is on the other side of the initial LCS, and it circles back around to the left. So what the LCS is showing you is that it's sort of folding in the time varying information as well to tell you about where material is going to be or not going to be transported. So it's showing us how B naught and C naught are really separating quite a lot in this example. But if you choose a different starting integration time, then even if you initialize A naught, B naught, and C naught at the same locations as with the previous plot, in this scenario, the LCS location has changed ever so slightly, and A naught ends up going to the right, and B naught and C naught end up over on the left. So the time T naught and the integration time from T naught to T final affect where the LCS is going to be. So I just want to make a comment here that I've been talking about sort of fluid flows, but of course the upper atmosphere becomes very low density. And so how do we even know that we can use this technique and that it's in any way going to be meaningful? To consider that, we can consider what the Knutson number is in the atmosphere. And this plot was produced by Balthazar and Bailey. The Knutson number is the ratio of the mean free path of an individual particle, on average how far it'll travel before colliding with another particle. And it's a ratio of that mean free path to the scale size of the fluid you're considering, or if you have something embedded in the fluid, the scale size of that object. So on the left-hand side, we're showing as a function of the altitude in the atmosphere, this characteristic mean free path length in meters. So this is lambda as a function of height. And on the right-hand side, also as a function of height, we're then considering the L, the ion flow scale size on the horizontal axis here. And the idea is that when the Knutson number is small, then it is a good regime in which to use classical gas theory, meaning fluid dynamics. When the Knutson number is much, much larger than 1, then you are kind of in more of a kinetic, a molecular flow regime. And so this would be a region in which we would not necessarily want to apply LCS analysis. So just to give you a sense of where we're talking about, the for this talk, I'll be showing atmospheric models and simulations from about 100, well, all of it's below 400 kilometers. And what that means is that we can be considering these LCSs if we're looking at scale sizes or grid sizes on the order of, say, 100 kilometers. So about 1 degree of grid spacing and so on. So as long as we're in that scale and larger, then we can be applying this LCS analysis. So the reason that we think it might be useful is because there are some important physics going on in the upper atmosphere. I'll start by talking about the charged particle layer, the ionosphere. The ionosphere consists of ionized, ionized atoms and molecules and electrons. And it's ranges from about 85 kilometers and up. It's created by UV radiation from the sun impinging on our atmosphere. And because they're charged particles, they are subject to electromagnetic forcing. The Lorentz force, F here, describes that a particle is going to be subject to an electric field. It will accelerate along the direction of an electric field. And if there's a magnetic field present and the particle is moving, it will it will gyrate around that magnetic field line. So when you have a crossed or perpendicular electric field and magnetic field, so E is pointing up and B is out of the page in this diagram, then charged particles will both accelerate in response to the electric field, and they would gyrate around the magnetic field. And so the combination of that motion kind of gives this spiraling motion with a net drift off to the right of the screen. And positive charges and negative charges both drift in the same direction. And that drift motion can be computed as it's referred to as the E cross B drift, and can be computed as the electric field crossed with the magnetic field divided by the magnetic field squared. So in the layers of the atmosphere of the ionosphere above 150 kilometers, this E cross B drift dominates the flow. There's not so many collisions with neutrals to impede this kind of drifting motion. So the LCS is going to occur, we expect, where there's sort of maximal stretching due to E cross B drift, because when we think about our flow fields, we're essentially integrating this E cross B drift when we trace particles along. So we're not really talking about an individual particle, which will be gyrating, but it's average drift motion. And so the flow map of the ionosphere would be starting with an initial particle and then tracing it as it's drifting along. In the thermosphere, the flow map is due to neutral winds, and we integrate the neutral winds over a particle trajectory. Now, neutral winds are sort of governed by the momentum equation. So we have the local derivative and then the convective term in the description of the momentum change. And the forces on the fluid will be due to collisions. Here, the collision frequency nu sub in between ions and neutrals, and the amount of difference between the ion velocity, E cross B drift, and the neutral velocity, U. And there will be other non-collisional effects as well. So the flow map, and therefore the LCSs, are kind of indicating a cumulative effect of ion drag and non-collisional effects as well. So I described how the calculation works, and there have been previously existing LCS calculations in GitHub in open source. But one of the things that I think is not always used is considering how the flow would move on the surface of a sphere. And of course, that's something that is very relevant for atmospheric flows. So in this work, we treat x1 and x2 as generalized coordinates. And they are, here we're going to use longitude phi and latitude lambda. And because those are our coordinates, our velocities, which maybe flow fields are ordinarily specified in meters per second in ground speeds, east and north, zonal and meridional, those velocities need to be converted to angular rates. This is a diagram showing if you have an Earth-centered, Earth-fixed frame E, how you measure longitude and latitude, and then at a particular point P, which direction local eastward is pointing, that's L hat 2, and northward, L hat 3. And so you take into account the radius of Earth to produce those angular rates. The other consideration is that the sphere is a closed domain. So what this means is that as you're tracing your particles across in longitude, if they cross over whatever your specified longitude limit is, let's say a particle at P, at this longitude at time I, you integrate it and then it ends up at less than minus 180, well, you need to wrap it back around on the other side of the world because that's what would be happening physically to that particle. And same thing over the pole. When the particle passes over the pole, it needs to come down on the other side, shifted by 180 degrees in longitude. Yes, in longitude. So particles need to be wrapped around. And so in addition to the FTLE calculation, we need to make sure that those particles stay in our spherical surface domain. And so we've implemented all of this in a tool we call the Ionosphere Thermosphere algorithm for Lagrangian coherent structures, or italics. And basically, there's you start off with a set of inputs. These are starting locations. Oh, that's interesting. This is your general velocity model. So here I'm showing for the ionosphere, but this would be any snapshots of flow fields that you have over time. So it could be for the thermosphere, or in this case, the ionosphere. And you get those velocities specified, you convert them to angular rates, and then you can propagate your particles forward in time, make sure they wrap around the Earth if they need to, and keep stepping forward in time. So we trace the particles through and until some final time, TF. And when we get our final locations, we can compute those separations using the Jacobian matrix, normalize them by the initial separation distances, and compute the FTLE values. And we can do this for every point on that spherical surface. And that will give us, and then when we map that, that will give us the location of the LCSs. Italics also, if you're just trying to do diagnostics, also you can put in individual tracers, those A naught, B naught, C naught, and see where those end up, and that can be provided as well. So, so we've been using italics along with various atmospheric model outputs to really try and investigate what the structures are in the upper atmosphere. So I'll start with ionospheric LCSs. And so each of these is a view of the North Pole with noon oriented at the bottom, and using an empirical model for electric field and the International Geomagnetic Reference Field for the Earth's magnetic field, we can compute E cross B drifts. We use those to trace our particles all the way through over a time span of about 3 hours. And then we plot these on a map, and you can see the yellow is where the LCS is. And so each of these diagrams has a different start time, T naught. But each of the diagrams has noon oriented at the bottom. And so this is noon. This is the LCS if you're starting at 6 UT with these models, 12 UT, and 18 UT, and integrating for 3 hours, I believe. So what we can see here is that there's sort of a recurring pattern. If you use this empirical model, E cross B drift indicates that there are LCSs at high latitudes that are sort of U-shaped. They're sort of U-shaped, and the opening is sort of on the anti-sunward side. And then if we initialize our tracers, A naught, B naught, C naught, I sort of picked this 12 UT one here for demonstrating that. The C naught hardly moves at all. It's actually sort of outside of the convection pattern. B naught drifts a little bit, about 30 degrees westward. And A naught, which is on the other side of the LCS, it's poleward of the LCS, actually travels quite a bit and across the pole over the time of this integration. And so there's sort of transport over the polar cap. If this pattern looks somewhat familiar to you, if you work with high latitude ionospheric dynamics at all, then it might cross your mind that these sort of U shapes on the left side, I'm plotting the LCS. So I've just picked out the yellow and I'm replotting it here with these magenta lines. They sort of, if you overlay them on a plot of electric potential, which is what gives rise to that electric field of the E cross B drift, there is some alignment there. But the difference is that with electric potential, you're getting a snapshot. So I've sort of mixed two things here. I'm a snapshot of electric potential, but a snapshot of the LCS that incorporates all the subsequent time and time variation of that electric potential. And then on the right-hand side is the same diagram as previously. So the top two plots show quiet time ionospheric LCS, and the bottom two plots show a geomagnetically active time period. And what we can see is that the ionospheric LCS, still U-shaped, but it's really expanded equatorward, away from the pole, and expanded outward. And so if we initialize tracers at exactly the same locations, wait, did I do them? No, I did not do them at exactly the same locations as before. Here, the tracers are at much lower latitudes, but they're still showing this. A and B are showing across the polar cap transport. And even C naught is showing quite a bit of westward movement. So that was all with empirical models of the electric field and the magnetic field. And again, we need those models because in order to do this calculation, you need velocity, you need velocity fields at some time, at multiple time intervals. A former student, Uriel Ramirez, built on Ningxia Wang's work and said, okay, well, what if I use SuperDarn and I look at the convection maps from convection patterns for SuperDarn, because Weimer's an empirical model, maybe we can get something more nuanced from having something that is data, a little more data driven on a epoch by epoch basis. And so what he found was that he found the LCSs in red. The blue LCSs are what you would get if you continue to use the empirical model. And what we find is if you use SuperDarn convection to model this E cross B drift, that the LCS can actually have a little more structure and variation. It's more of a W here than a U. And this figure of the North Pole is oriented a little differently. The dashed line shows you where local solar noon is. So we also wanted to investigate, does this have any potential implications for how plasma is or is not going to be transported? One of the features in the ionosphere that we're often interested in at high latitudes are called polar cap patches. So these plots show in the color scale density of plasma, essentially. And so a polar cap patch is a region of high plasma density. It's sort of identified with this red dot here. And on the edges of these, you can have various instability effects, turbulence effects. These can have impacts on communications and navigation systems that rely on radio frequency transmissions. So plotted in black are the LCSs for different initial times. So what we did here is we see, okay, there's a polar cap patch. If we go earlier in time, can we see where that polar cap patch originated from? And so each of these plots is going earlier in time respectively. And what we find is that if there is plasma that is poleward of that W-shaped LCS, then that's the source of that plasma that can form polar cap patches. And so we think that there is, a significance to computing where these LCSs are for what they might say about where polar cap patches, when and where they might be expected. Moving on to the thermosphere. So the neutral atmosphere from, say, 100 kilometers and up or so. In the thermosphere, we used an empirical model when we were first starting out, and we were sort of looking at different layers in the thermosphere. So the upper left plot is sort of a Mercator projection of the FTLE map at 150 kilometers. Below it is 250 kilometers. And on the upper right, 350 kilometers on a geomagnetically quiet day. And there are tracers initialized, and how they travel is actually easier to see if you look at the North Pole plots. So what we can see is that going from 150 to 250 to 350, the LCS structures differ with altitude, and they do become stronger, sort of more pronounced at these higher altitudes here. So for 250 kilometers, we contrast this quiet day on the left an active day, a geomagnetically active day on the right. And you can see that with the occurrence of geomagnetic activity, there is a lot more structuring to the thermosphere, the neutral thermosphere's flow structure. And that also manifests in the way that the tracers move over time. And again, you can see those with the polar North Pole view plots. So what we can see here is that we expect thermospheric LCSs will vary with altitude and with the level of geomagnetic activity. So seeing some similarity and seeing that response to geomagnetic activity in the thermosphere, Ningqiao Wang, who is now a postdoc at Hampton University, used TIE-GCM to take advantage of a coupled first principles model that includes the behavior of the thermosphere and ionosphere sort of self-consistently. And on the top, we're plotting in a sort of stereographic view the neutral wind LCSs looking from the noon sunward side. So we're looking at the day side on a quiet day and on an active day. And across the bottom are the ionospheric LCSs on a quiet day and an active day. And so you can see that they have some overlap, some relationship between where those are located, and they both do tend to shift equatorward during geomagnetic activity. And then, so we've extended this and really been trying to push and see what we can find out going to lower and lower layers. And so this is a study led by Lynn Harvey, looking at the split Arctic vortex. And so on the left-hand side, top plot, this is the WACMX DART model. And it's showing at the 0.001 hectopascal pressure level, the geopotential height. And overlaid with that is the fact that this Arctic vortex does actually seem to snake up and around as you go through the altitude layers. So the light gray is at 30 kilometers, I believe, altitude, and the medium gray at 50. The black is at 70, and then by the time you're at about 90, you see the WACMX start here. On the right hand and on the upper right hand side, in grayscale, is the FTLE map at that 0.001 hectopascal, meaning right around 90 kilometers. Okay, and so the grayscale, if you look at the darkest gray, those are the maximum LCS values, and just to enhance the view, it's sort of got a dashed pink line here to kind of show you what regions are being separated. And for additional, there are some additional tracers here that are each initialized and with a different color where they're all initialized around the 65-degree latitude circle, and where they travel over that time is plotted as well. And so you can see right in here that these are confined, the red, orange, and yellow are confined into that vortex. On the bottom plots, we can see observations from SOFI and ACE-FTS satellite data of enhanced values of NO, nitric oxides, and they are enhanced in that region of where we suspect that confinement is happening, and it's sort of channeling and enhancing descent. And I believe the bottom right plot is showing temperature variation as well, which is also an indicator of this descent. So this is an interesting example of how it may be able to help us with understanding nitric oxide location and movement. So then we moved on to an additional study, coming back to that original question. And I said, oh, you know, the space shuttle dumps all this water vapor. And then there are observations, for example, from the GUVI satellite of that water vapor over the next couple of days. Can we use models? So in this particular case, the whole atmosphere community climate model with the extension into the exobase.
It seems like we maybe lost Sabani.
Yeah.
And several other people as well. I don't know what happened there. Sabani, you're back?
I am back. I'm not sure what happened there either. I apologize. Let's see. I'll go back to presenting. Please let me know. I think we left off on this slide. Can everybody hear and see me okay?
Yes.
Yes.
All right, great. Okay, so we tried this out for an April 2002 shuttle launch that's shown across the top. The LCS predicts containment and the water vapor and grayscale show containment. Great. So then we tried this for an October 2002 shuttle launch. And here, A naught and B naught are sort of separated by an LCS ridge if you use SD-WACM-X on the left. And those are plotted over here on the right. But what you see on the right is that the tracers don't actually go where the water vapor is observed. And admittedly, this is a big ask. This is kind of at the limits of what I think is state of the art in upper atmospheric modeling. But so it's a very stringent test to ask, what is this predicting? Can we use this and compare it to observations and so on? But we wanted to investigate further, you know, why might this be happening? Is it specific to a particular model? So in this example, we tried both SD-WACM-X for a July 2006 shuttle launch and WACM-X DART. So WACM-X DART has a different data assimilation scheme that does ingest measurements at higher altitudes. I think SD-WACM-X, the data are assimilated up to about 50 kilometers, and then it becomes free running above. And so what we see here is for this same event, same initial time and integration time, we get pretty different patterns of what the Lagrangian coherent structures are over the northern Atlantic, and different predictions of where those tracers go as well. And then when we compare them on the right-hand side to where the GUVI observations are, they're sort of spread across the whole Atlantic. I'm not sure if you can see this. It's pretty light gray, and it's not really clear which of these models might be doing a better representation of that particular event. So we took these two models and tried them for a different shuttle event where unfortunately we don't have the GUVI observational data. And we're looking at this 100, actually I guess about 110 kilometers altitude with SD WACM and WACM-X DART below. On the left-hand side at 110 kilometers and the right-hand side 60 kilometers. And what you can see is that the LCSs differ a lot at 100 or so kilometers, more so than they do at 60 kilometers. And you can see this in the tracer movement as well. For both of these, the tracer movement is relatively consistent for 60 kilometers, but not so much at that higher altitude. So I think this is sort of a lesson we've learned here, which is that if we're going to be using models for really looking at material transport in the lower thermosphere, we need to be cautious about that. So this is work that we are trying to extend italics into because the question we're interested in is what happens. The big challenge right now is pretty much everything I've shown has been from model output velocity fields. And they're constrained in different ways by the data, but this is not like a laboratory fluid environment where you can just visualize flow with whatever sensors you have right there and have a complete specification strictly from data. So what happens if you do have data or flow fields, but they are over a restricted domain? You don't have it globally. And so for part of that, we've been trying to develop this finite domain FTLE calculation. Essentially what happens is if you only have a finite domain over which your velocity is specified, if particles go out of that zone, out of your domain, then you don't know where they go next, you don't know how to integrate them, and you get very strange Lagrangian coherent structure artifacts that are not actually part of the flow. And so the solution is to actually smoothly transition the flow to something that is a linear uniform flow outside of the domain where you have measurements or where your velocity is specified, because a uniform linear flow produces no LCSs. So we're starting some work on that. We went back to our thermosphere. This is a picture of the northern hemisphere's LCS at 250 kilometers and said, okay, what if we didn't have the entire model, but we only used the northern hemisphere and we sort of cut it off between 35 and 80. And then we use a transition region inside the box to smoothly taper the velocities. And so this is sort of an example of this. We sort of smoothly taper to an average zonal flow outside of the boxes or beyond the limits. And is everybody still hearing me?
Yes.
Okay, great, thank you. So this is basically kind of where we are right now. If you have a global flow specification, this is sort of what the idealized case would look like. If you just crop those velocities and don't change anything about your calculation, then those particles that go out of the flow field, you don't end up with meaningful FTLEs, and therefore your Lagrangian coherent structures get all messed up. And so this smoothing process outside the region really does preserve the LCSs in the interior. So we have developed something that will help us to have a latitudinally restricted flow and have yet to move on to the longitudinally restricted. And also going to 3D, you will need to have some sort of altitude restrictions as well. So in summary, what I've been talking about here is the use of empirical physics-based and data assimilative models of the ionospheric drifts, thermospheric neutral flows, getting down close into the mesosphere and lower thermosphere. And they indicate that LCSs exist. And in in several cases, we were able to compare LCSs to observations of material species, polar cap patches, Nox, and we can use them to identify regions of differing transport and of confinement. But what we found also is that different models or means of data constraint can give quite different results, particularly at that 100-kilometer altitude range. And there's none of these results are completely data-based because we can't do flow imaging of our entire upper atmosphere yet. So with that, I'd like to thank you for your time. My email address is at the bottom, and I'm happy to take questions.
Thanks, Yvonne. Does anyone have any questions? So Dan Marsh has a question. Go ahead, Dan.
So I'm sorry if I missed this, but is this calculation done in the XY plane or in the Y, so the YZ plane? Are you doing it at each level? Because I was thinking when you were showing that very first picture, that was sort of like, oh, I was thinking more that's like the YZ plane, and that you're having this sort of large auroral heating and you're getting these big circulation patterns. And also when we're thinking about NOx transport, we're also thinking about, descent and those sort of things. So is this a 3D calculation or a 2D calculation at each level?
No, so,
what do you do?
Yeah, so right now it's a 2D calculation, and if I can come back, I think, so in the cartoons, I'm just showing them as X and Y, but for the atmosphere, those X and Y are latitude and longitude. So it's the surface of a sphere. I'm trying to figure out if I can, here. So we're sort of taking, you can think of each one of these, if I choose a different altitude, I'm choosing a different shell that I'm computing the LCS over. So we're interested in working on a 3D calculation, but it gets computationally more costly. And what's the other aspect? But I think it's probably necessary. One of the things that we found is with this altitudinal variation that, that there are wind shears, and that causes different locations for LCSs. And so to have a complete picture, you'd really want to try and get that third dimension. So
yeah, I think some of the discussions over the water vapor transport indicate that there are potentially some very strong wind shears in the thermosphere. This water quite large distances.
Dan, you're a bit hard to hear. I don't know if you can repeat your point.
Sorry, maybe it's not picking up my microphone. Hopefully that's a bit better. No, I was just saying in terms of the shuttle water vapor transport that there's been discussion that there had to be very strong shears in the atmosphere that could potentially move a plume, to the South Pole. Metal layers show up, 3 days after a launch, and so I'm thinking you have to take into consideration sort of these strong shears, and just in that particular problem at least.
Yeah, so I don't disagree with that. I know that there are strong shears kind of at these altitudes. And so so the thing I'm not sure about is whether, converting italics to being 3D would by itself be sufficient, because I think then you still have a choice of which model that you get. And what we found is that you could get pretty different transport, just even in 2D, with two different models, or Whack-A-Mechs constrained in two different ways. But yeah, that would be.
You have to try that in the YZ.
YZ plane.
Latitude, height.
With latitude and height. No, I don't think we have, and I'm not sure. So all of these runs, the Whack-A-Mech start runs were produced by Nick Peditella, and I believe he did store that information for the, so that would be one of the variables that I think you provided, Nick, but we haven't done that. And then so you could do a slice along that dimension and see what that looks like, and that would, I think that's what you're asking. Are there LCSs at different altitudes on a particular latitude slice?
Yeah.
Yeah, no, I think you could do that with, I guess you would need vertical wind and meridional wind.
Right.
I'm not sure how much, right? You know, there's a strong zonal wind, so how much missing that would have an impact. If you take a sort of, fixed height, you can maybe more assume that there's less vertical transport.
Right. So that would be kind of this finite domain problem. If you just take sort of one longitude sheet and your particles are going at all eastward, I mean, maybe you're suggesting discarding that eastward movement, but I'm not sure then.
Looking at a zonal mean framework or something.
So look at a zonal mean of the meridional wind. Yeah, but then the averaging, there is a lot of variation sort of going around. So I don't know, it might be harder than to capture one particular shuttle event, I would imagine. Like if you're zonally averaging. I'm not sure. But it's an interesting question, and I know I focused on the Northern Hemisphere, but at least for some of these studies, we did investigate the Southern Hemisphere as well. And these, there are, in the Thermosphere, there are definitely seasonal, you can see the summer versus the winter hemisphere and things like that.
Are there any other questions for Sapani? I'll ask one. Just curious, with this sort of limited domain, what do you see as the main application there? Like for use on like a regional type of model, or for using like if you have a regional network of observation?
Yes, exactly. The latter is kind of what I had in mind. So I know, I know that people have set up ground-based systems for, so in particular, I guess Mark Conde has these scanning Doppler imagers that he sets up to look at convection above Alaska. And what I had originally thought is, okay, it'd be great to look at how those are varying over time and see what's happening to that flow structure. But the problem is that they go out of the field of view if you trace through. So we haven't really found a good solution for that yet. But my own interest would be in moving towards something that is very their measurements of the vector velocities over time. But that said, I think everything that we've shown here has been model based, and you can run a model, compute the LCS, and then compare it to what maybe your real-time observations of plasma enhancement are, and maybe that ends up being a forecasting system. And so that's even if you don't have completely data-driven flow fields, then I think models can be very useful in this sort of diagnostic way.
Last chance for any other questions. If not, then thank you again, Subhani.
Thank you. Thanks, everyone. Thank you, Dr. Marsh, for your questions. Nick, thank you.
Thank you.
I'll stop sharing here. There we go.